Second chapter, first section. You have three objectives in this section. Develop and use properties of the natural logarithmic function. Determine the domain and range of logarithmic function. Solve the logarithmic equation. It is neither algebraic nor trigonometric, but falls into a new class of functions called logarithmic functions. This particular function is the natural logarithmic function. The natural logarithmic function has the following properties. First, the domain is from 0 to infinity, and the range is from negative infinity to positive infinity. The function is continuous, increasing, and one-to-one. The graph is concave downward. First of all, you need to recognize what is the natural logarithmic function when the base is equal to exponent, where the value of exponent is around 2.7. The logarithm is known as natural logarithm. For example, when we have log of x, base is exponent around 2.7, then can be written as natural logarithmic function of x. And if we have log of x, the base is 10. This is a common use, base. So you can just write log of x. A function defined by this expression is a logarithmic function. The expression natural logarithmic function of x is defined only for all positive real numbers. Therefore, the domain of a logarithmic function is a set of all positive real numbers. We can verify this statement. First, write down the function. We say fx function equal to natural logarithmic function of x. And you contract table. And exactly same as the method you learned in first chapter, first section. We set the domain of x. You can start from -2, and you can check with your calculator where this function button is under the constant button. So when you substitute -2 into this function, you will find that the output is undefined. And for -1, also is undefined. 0, undefined. 1, 0. 2 is around 0.7. 3 is around 1.1. and so on. And you look at the domain between 0 and 1. And you can try to check the value between the 0 and 1. Let's say x equal to 0.5. And fx is around negative value 0.7. You also can try the other values, for example 0.0001 or 0.9, 0.8 something, 0.9 something, and so on to observe. Okay, what is the output? And based on here, our table here, so we can see actually the function is defined only, okay, the x is from 0 to positive infinity, but exclude the 0. So you can conclude domain is from 0 to positive infinity, exclude 0, meaning that we start from 0 point something. After you have constructed the table, you can scale out the graph. Based on the table you have constructed in the previous slide, you actually can scale out the graph. And this is a curve of this function. From the table, we have verified our first property. The domain of this function is from 0 to positive infinity, where the 0 is not included. And for the second property, the function is continuous. You actually can continue your parameter of x extend to 100, even 1000. You will find that your curve is continuous. And if your x value is getting closer to 0, your value is getting smaller and smaller. Curve is continuous going down. And the function is increasing from left to right. And the function is one-to-one function because we can apply the vertical line test. There is just only one y value. For the third property, the curve is concave downward. So based on the curve here, you can see. So the curve is concave downward. Or you can say the curve is facing down. Second property, we have verified this function is one-to-one function. So meaning that this function has inverse function. And we say the exponential function is an inverse function of natural log function. Show you. Just based on the previous table, we have natural log of 1 is equal to 0. And we also have natural log of 2 is around 0.7. And natural log of 3 is about 1.1. And you know that the 1, 2, 3, they are input. It's x value input. And 0, 0.7, 1.1, they are output. You can say y. I'll look at the inverse function. Now, we call back the first chapter, what is the inverse function? The output will become input, and the input will become output. You can verify with your calculator. Exponent 0 will equal to 1. And exponent of 0.7 is about 2. Exponent 1.1 is about 3. Where 0, 0.7, 1.1, they are output of this natural log function, but they are input of exponential function. So compared to here, this is a y, right? But in this part, play as an input row, and 1, 2, 3 they are x, but play as output row. So we have verified. And you actually can look at this curve for the second statement here as x tends to 0, meaning that x approaches 0 but not equal to 0, not touch and on 0, because when x equals to 0, the function is undefined. So you can see the curve. You can try to test. Your curve will continue going down. So y tends to negative infinity. The value is getting smaller and smaller, while the x increases, the curve increases. And from the curve, you will find that y, the range, is valid for all real value along this y-axis. The first example, sketch the graph for each of the following logarithmic function and determine its domain and range. We have fx equal to natural log of x minus 2. Everybody knows x minus 2. The value of x minus 2, the value here, cannot equal to 0, because when the x minus 2 is equal to 0, meaning that this function is undefined. So we should set x minus 2 greater than 0. So we can obtain the x domain. The x should greater than 2. After we obtain the domain, since the question requires us to sketch the graph, you can determine the x-intercept. When to obtain the x-intercept, y is equal to 0. So you can let the fx equal to 0, then you solve for the x. Or I show you here the original function fx equal to natural log of x minus 2. So for the x-intercept, let y equal to 0. So can be written as natural log x minus 2 equal to 0. And to eliminate the natural log function, I use inverse function. So both sides, I put in the exponential function. So I will have x minus 2 equal to exponent 0. So we try to compare the input. Now will become the output of this exponential function. The output 0 from natural log function now become the input of exponential function. Or in other words, we say we take this natural log function to right side, so we become inverse. And exponent 0 is equal to 1. So x equal to 3, x intercept. Next step, to obtain asymptote line, you convert the function notation to explicit form. Change the fx to y. This is the original function. And same. To eliminate the natural log function, I put in the inverse function at both sides. So I will have exponent y. Then eliminate the natural log function. And I solve for x equation. Now I obtain x equation. The asymptote line when y tend to negative infinity, x tend to 2. Now I show you. You change the x equation. X tend to exponent y plus 2. After that, when y tend to negative infinity, to get this step, y tend to negative infinity. What do you understand about this y tend to negative infinity? Y is our curve. So when the curve is going down, continues going down, so is there the barrier? So this is a point that we need to study. The barrier is the asymptote line. Now, I show you another table. So, okay, just particular for this, y tend to negative infinity. So look at this term, exponent y, and y tend to negative infinity. Okay, we study this. I contract table now. We have y, and we have exponent y. Y tend to negative infinity, so meaning that the value is getting smaller and smaller. For example, -1. You can check your calculator. You substitute -1 into exponent function. You will have 0.3678. And how about -5? You will have 6.738 times 10 to the power of -3. -10. We have 4.54 times 10 to the power of -5. And how about 10 to -100? And how about -1000? You observe the value here. The value is getting smaller. So when the y value getting smaller, the value here also getting smaller. So almost equal to 0. So that is why the value here is almost equal to 0 when y tend to negative infinity. So we can write x tend to 0 plus 2 and x tend to 2. So we obtain asymptote line x equal to 2. So x equal to 2 is vertical line, is vertical asymptote, and is a barrier. The curve cannot touch. So we can conclude x equal to 2 is an asymptote, and as x increases, fx increases. So you can extend your x domain and you can find that your curve is increasing. So we can conclude our answer. The domain of this function x must greater than 2, and for the range of this function y is the real number on y-axis. For the second function, we have natural log of x squared minus 9. So the value here should greater than 0, not equal to 0. So x squared minus 9 should greater than 0. And we try to solve this quadratic inequality. We actually have covered this part in our first week revision. I factorize this x squared minus 3 squared. And I factorize, I will have x plus 3 and x minus 3. And from here, I can get my critical values. X equal to negative 3 and positive 3. After I have critical values, I can draw my number line. My x in this value is negative 3 and 3. So for the first line, represent the first factor, negative 3. Okay, the sign is greater than 0. So my line should towards right. Exclude negative 3 because the sign not include. And for the second factor, my second line also towards right, and I fill by positive, and the rest negative. So the first factor multiplied by the second factor, so the result of this multiplication yields plus, plus minus plus, minus minus plus, and based on the required from this inequality, our result should be greater than 0 because greater than 0. So our domain is to make this function valid, or we say define, the x value should be greater than 3 and less than negative 3. So you can conclude, for example, this is a 0 and 3 and negative 3. The value here only, and here this side after negative, before negative 3, sorry, okay, before negative 3 only, okay, can substitute into this function. The value between here can make the function undefined, and this domain, this form, can be written in this form we call absolute value function. Okay, I try to explain a bit this absolute function. So the meaning of this absolute value function of x greater than 3, meaning that at positive side, 3 units from origin. So from origin, mass greater than 3 units from origin. So only valid here. And in negative side, also the same. In negative side here, mass greater than 3 units from origin. So the region also same as this form. We have find out the domain. Now we can determine the x-intercept. For the x-intercept, you let y equal to 0. So we have natural log of x squared minus 9 equal to 0. Then you solve. So same, you bring the natural log to right side. So we will have inverse function. So we call exponent function. And exponent 0. So where the exponent 0 is equal to 1. And we move negative 9 to right side. So we become positive. So 1 plus 9. And x squared equal to 10. So x. Okay, so I continue here. So x will equal to plus minus radical 10. So here our x-intercept. Have x-intercept. You can see the working actually exactly same as the first example. From the function notation, we convert into the explicit form. And to eliminate this natural log function, we use inverse function. So we put exponential function at both sides. So left side we will have exponent y, and right side no more natural log function. We have x squared minus 9. And we solve for x equation. For this part, to get the asymptote line, we study the curve. When the curve continues going down to negative infinity, going down, is there the barrier? So you refer to my explanation in the previous slide, then you continue to obtain asymptote line. So the first asymptote is x equal to 3, and the second asymptote is x equal to negative 3. So we have a 2 asymptote line. And based on the curve here, the range of this function is valid. Okay, it exists for all the real number on y-axis. Look at the properties of logarithmic function. If a and b are positive numbers and n is rational, so for the first one, natural log of 1 equal to 1. This one we have proven. And natural log of a multiply b can be written as natural log of a plus natural log of b. And for the third property, we have natural log of a power to the n can be written as you move down the power n to in front. So we have n natural log of a. And for the fourth property, natural log of a divided by b can be written as natural log a minus natural log of b. Be careful with the second and the fourth. The common mistake made by students we have, for example, we have natural log of a multiply natural log of b is not equal to natural log of a plus b. And for the last property, natural log of a divided by natural log of b is not equal to natural log of a minus b. Please take note. Look at this example. Natural log of 10 over 9 equal to natural log of 10 minus natural log of 9. And for the b, natural log of radical 3x plus 2. First, you can rewrite this expression, okay, for the radical part to the power to the half. And we can use the third property, where the power we can bring to in front. Look at the C. We have natural log of 6x over 5. So can be written as natural log of 6x minus natural log of 5. We use a fourth property, and where the natural log of 6x can be written as, because they are in the product form, natural log of 6 plus natural log of x minus natural log of 5. For D function, look at the input of this function. The input given is rational function. So since you know this is a rational function, then immediately use the fourth property. The fourth property is the division we convert to minus. So now here we perform, and after this you can see this power here can move to in front. The third property, and for the second property, you can see the input of this function is product form. They are in the product form, so you convert into the plus. Use the second property and expand into negative. And for the last term, has power 1/3. So we can use the third property, move the power to in front. When using the properties of logarithm to rewrite logarithmic functions, you must check to see whether the domain of the rewritten function is the same as the domain of the original. For example, the domain of fx equal to natural log of x squared. Look at this graph. The domain of this function is all real number except x equal to 0. You can try to substitute the value of x equal to 0 into this function, where the function is undefined for x equal to 0. And look at the negative side. Just take one value of negatives. Let's say you take the negative 2. You substitute into this function, meaning that you will have natural log of 4. So meaning that this is a valid. It's undefined in negative side. And for this original function, if you apply the property and the power to, we move to in front. Look at this one, we move to in front. And we have two natural log of x. And for this function, the domain for this function is just only for the positive real number. So only at this side. Because when you substitute the negative value into this function, so this function is undefined. Logarithms. We know that the number 9 can be expressed in the form 9 equal to 3 power to the 2. Where 3 is the base and 2 is exponent. We may also express 9 equal to 3 power to the 2 by using logarithm notation as log of 9 base 3 equal to 2, where the number 3 is called the base of logarithm. And we read this expression as logarithm of 9 to the base 3 is 2. In general, if a and x are positive real numbers and n is any real number, for example, x equal to a power to the n, then the logarithm of x to the base a is n. So look at this. X equal to a power to the n can be written as log of x to the base a equal to n. Look at this example. So let's say we have a equal to b power to the c. This expression can be written as log of a to the base b equal to c, and 1 equal to x power to the 0, because anything power to the 0 is equal to 1. And we can express this by log of 1 to the base x equal to 0, and a equal to a power to the 1, same as log of a to the base a equal to 1. The logarithm of 1 with any positive real number as base is always 0. The logarithm of any positive real number with the same positive real number as the base is always 1. For the law or the properties of the logarithm totally same as the properties of natural logarithmic function. Try the third example without using a calculator. Evaluate log of 1000 to the base 10. So the first step, you can rewrite the original expression, and then you can convert the 1000 to 10 power to the 3. And after this, you can move the power to in front. So we have 3 log of 10 to the base 10. For this step, the logarithm of any positive real number with the same positive real number as the base is always 1. So we have the answer is 3. And for the next example, express log of 2 plus log of 3 plus log of 5 as a single logarithm. So we have log of 2 multiplied by 3 multiplied by 5. So we have log of 30. It is useful to know how to change the base of a logarithm to a suitable base in order to be able to solve logarithmic equations or to prove a logarithmic equality. To change the base of a logarithm from a to b, we can use the method as below. Let's say we have log of m to the base a is equal to x. Then we move the log function to the base a to right side. So we will have exponential function at our right side where the base is equal to a. And taking both sides for the log function base b. So we have, I show you for this step, both sides we apply the log base b, so meaning that left side we have log of m base b, and for the right side, before we get this expression, so this is a working, we have log of a power to the x base b, and the power x can move to in front. So we got this step. And in order to get the x, so we move the log of a to the base b to other side. So we have x equal to log of m to the base b divided by log of a to the base b. This is a x. We have obtained the x, and the x also equal to log of m to the base a. As a result, we can write log of m to the base a equal to log of m to the base b divided by log of a to the base b. For another rule, we base on the previous rule. We let b equal to m. So the b here can be written as m, and the b here also replaced by m. So where the log of m to the base m is 1 over log of a to the base m. So we have log of a to the base b equal to log of a to the base c divided by log of b to the base c, and also can be written as 1 over log of b to the base a. Look at this example. Solve for x in each equation. For a, you have 3 power to the x equal to 1 over 81. So you can see your left side term is an exponential function. The base is 3, so we should apply the logarithmic function to the base 3. So now we have log of 3 power to the x base 3 and equal to, same for the right side, log 1 over 81 to the base 3, and you can see here you actually can simplify because they are inverse function. The log base 3, the exponent base 3, so you just only have x. Or as I say in previous, we just move the 3 to right side. The 3 here is a base of exponential form. We move the other side, will form inverse function. So will become log function, the base 3. Okay, so we only have x. And then some more, 1 over 81 can be written as reciprocal form, where 81 is equal to 3 power to the 4. So we have a minus because it's reciprocal. Okay, so after that, look at this one. the negative 4 is a power. So we can move this negative 4 to in front. So we have negative 4 log of 3 to the base 3. So which is equal to 1 for this side. Log 3 to the base 3 is equal to 1. So lastly we have negative 4. And for the B question, log of x to the base 2 equal to negative 4. For the B question, to solve this equation, you can apply the exponential function to the base 2 to each side of the equation. Write back the original equation. You can see your left side is the log function. So to eliminate the log function, you should apply the inverse function. So it's exponential function to the base 2. Why is base 2? Because the log here is base 2. So we apply both sides, meaning that log function no more. So your left side just left x only. And for your right side, you will have exponential form because you apply the exponential function. So to the base 2, you can see here is a base 2, then power to the negative 4. And negative 4 meaning that it's reciprocal. So it's 1 over 2 power to the 4. And the answer is 1 over 16. To solve the C, you solve this equation, you can change the base to the 2 or x, either one. You can look at the first term and the second term. For the first term, the log function is base 2, but for the second term, the log function with the base x. You can choose either one. Then form the quadratic equation. So let's say I choose the base as 2. Now, if I selected my base as 2, so I remain the first term because it's already base is 2. So for this one, I use the rule that we have proven just now. Log of 2 to the base x can be written as 1 over log of x to the base 2. Then, the first term and the second term, they have the same base already. So we just can solve. The next, we let y equal to log of x to the base 2. Then, we can write 2y minus 1 over y minus 1 equal to 0. So how are you going to solve this equation? The whole equation can be multiplied by y. So we form quadratic equation. So we solve quadratic equation. You factorize and you let equal to 0 these first two factors. For the first factor, you let equal to 0. So we have y equal to negative half. And don't forget to change back your y equal to log of x to the base 2. Because we are solving the x, it's not solving y. Then you can see this expression, this equation actually already back to our part A. So when we have log function, meaning that we should apply the exponential function at both sides. This is a log function to the base 2, so we apply the exponential function to the base 2. So for the right side, no more the log function, and for right side, we have exponential form. The base is 2. And you can rewrite your answer as reciprocal form because negative, the power here is negative. And we have 1 over radical 2. And you should multiply the conjugate. So radical conjugate is radical 2 over radical 2 for this value. You can look at this conjugate. The value of this conjugate is equal to 1. So when our answer multiplied by the 1, our answer still remains the same. We're not affected. So 1 multiplied by radical 2 is radical 2, right? And radical 2 multiplied radical 2 is 2. Now I show you once. Radical 2 multiply radical 2. So radical is the power to the half. Multiply. So look at this one. For these two exponential functions, they have the same base, so we can add their exponent. So half plus half is equal to 1. So we got the answer is 2. And for the second, we let the second factor equal to 0, so we have y equal to 1. And make sure you change back the y. So we have log of x to the base 2 equal to 1. Then same, we apply the exponential function. So to the base 2, and we have this one at our right side. Then the answer is equal to 2. So we can conclude our answer. Our x value is equal to radical 2 over 2 and 2. And you can recheck your answer when you substitute back these two answers into your original equation to verify whether your answer is correct or not. Look at the important result of inequality involving exponent and logarithm. For the first case, we have for a greater than b and c greater than 1. We just say a is 4 and the b is 3 and c greater than 1, so we say 2. Look at the statement. C power to the a greater than c power to the b. Is it true? So c is 2. Look at the first statement. C is 2. Power to the a greater than c is 2. Power to the b, power to the 3. So it is true. And for logarithm, we have log of a is 4 to the base c 2 greater than log of b 3 to the base 2. And you can use the same method to verify the second statement. Look at the last example. Find the set of values of x which satisfy 4 to the power of x greater than 150. The first step, you can rewrite back the original inequality, and after that, taking both sides of logarithm to the base 10. So we have log of 4 power to the x. And look at the x, the power. We can move the x to in front. And in order to get the x value, we move the log of 4 to right side. And be careful in this step. Because of log of 4 is positive value, so the inequality sign remain. But if we are moving the negative value, the inequality sign should be turned over. Lastly, we get the answer. And since the question requires us to find the set of value of x, So we should write our answer in this form.